Hello everyone, my name is Duffie Cooley, and I am a field CTO at Isovalent, where I get to work on Cilium and eBPF. I am a CNCF ambassador, where I get to help folks with all sorts of wonderful things, and I am a member of SIGHONK, a hacker crew, with Ian Coldwater, Brad Giesemann, and Rory McCune. Recently I've been doing a lot of video streaming with things like TGIK.io, cloudnative.tv, and Echo Office Hours, which is a great place to learn more about eBPF and what's happening in the ecosystem. You can check it out at git.io/e capital CHO. If you're working in the eBPF space and you want to hang out with me and maybe join an Echo session, definitely let me know. I can be found most everywhere as Maui Lion. And that's because I grew up on Maui and I like big cats. All right, let's get started here. So in this talk, I'm actually going to introduce a few concepts, many of which I'm hoping are be pretty familiar with you, to you at least. But if they aren't, then maybe you'll learn something. And even if you're not new at this, even if you've been around a while, it's always kind of good to have a refresher for this kind of stuff. So we're going to kick it off with what is a container. So a container is just a Linux process. Like any other process on any Linux system, this is actually one of my favorite visual representations of a container because it points out that every running process on a Linux system has namespaces associated with it. A C group that it's running under, an IPC namespace, mount, net, PID, user, and UTS namespaces. If you've been working with containers for a while, you're familiar with some of these things. But every process on the Linux system will be associated with some set of them. When you SSH into a Linux system and you type ps-ef, and you may see a number of processes running, and this view is a view of the host PID namespace. And so from here, you can see every running process on the system. When you type ip-link show, and you see a bunch of the interfaces that are actually associated with the actual host, the physical machine, then or virtual machine for that matter, then you are actually experiencing a view of the host's network namespace. And generally, when we create a container, we create a different network namespace for the process in which that container is containing to sit in. And so it would only see the network interface associated with that process. And we create a new PID namespace such that when you exec into a container and you type ps-ef, you're only seeing those processes that have spawned since the container process or the initial process of the container spawned. Pretty neat stuff. So that's effectively a pretty good summary of what a container is. Let's move on to a syscall. What is a syscall? So think of syscalls as an API that programs use to interact with the Linux kernel. When we write code that needs stuff like memory or to open a file or to read an environment variable or to bind to a port, we write in an abstraction that will eventually result in a system call that is forwarded to the Linux kernel system call interface. And if you want to see what system calls are happening for a process, one way to do that is with BPF. There's tons of really great tracing tools available. I mean, I recommend checking out kubekettle-trace or some of the BCC stuff. There's tons of great talks out there on how to do this. But let's use strace to see what calls have been made by this curl command. So I've made a curl to google.com, and I've truncated it a bit, but we can see that we're getting a bunch of memory maps, we're getting some close, we're getting some new FS stats, we're getting openat, basically trying to read files from the file system. We're getting the read syscall and the poll and futex. A number of different syscalls at a number of times running called by that particular process, just the single process of making a curl call. What's interesting about this is that system calls are one place where we can actually harden what a process can actually do inside of a container, or just generally even outside of a container. If we provide a seccomp profile for a given process, we're basically giving a list of system calls that process can make, and maybe and what to do if that system call does try to make processes or system calls that are outside of its scope. So if I limit it If I say this process cannot make a kill command, then if it tried to do a kill command, it would get an error back. But to do all of that, we kind of need to know a place to start. So, a place to start, system calls can be grouped roughly into 6 major categories: process control, file management, device management, communication, that sort of thing. There are currently 345 system calls defined in the x86-64 architecture of the Linux kernel. And that's just for the x86 architecture. There's a different number for the number of system calls associated with the ARM architecture. And what's interesting is that when you make a system call, it's represented by an integer that we can map back to what system call based on the architecture that you're running. And that integer may be different whether that system call came from an ARM machine or is made against an ARM kernel or made against an x86-64 kernel. That integer may be different. That map may be different depending on the architecture that you're looking at. So, pretty interesting stuff about system calls. So, we talked a little bit about system calls. We talked a little bit about processes. If I were there in person, I would ask this question. I would say, what is a capability? Do people here in the room understand what a capability is? A Linux capability specifically. If so, raise your hand. But I'm not there to see you, so don't do that. Instead, give me a thumbs up or something on the virtual side of things and let me know that you actually know what a capability is, or ask me questions inside the chat. I think that the man page is a great place to start on this particular subject. It actually has a really good way of a really good overview of permissions, of authorization for the Linux systems in general. And it goes on to say that for the purpose of performing permission checks, traditional Unix implementations distinguish between 2 categories of processes: privileged processes, whose effective UID is 0, or referred to as superuser or root, and unprivileged processes, whose effective UID is non-zero. Privileged processes bypass all kernel permissions checks, while unprivileged processes are subject to full permission checking based on the process's credentials. What is the effective UID, GID, and supplementary group list? You've interacted with this on the file system. It's a pretty good, easy way to put it in your head, right? Like if you SSH into a system and you touch a file inside of your home directory and you change the permissions of that file in your home directory such that only you can use it or execute it, and I SSH in and I'm a different user completely, and I try to read your home directory and manipulate that file, I will only be able to do that if we share that same group access, or if you have given me permission to that file as the creator of that file. Now, if I SSH in as root, all bets are off. I can do anything I want with that file because I am now a super user or a root user on that host. Capabilities are much like that. So starting with kernel 2.2, Linux divides the privileges associated with that root or that super user into distinct units known as capabilities, which can be independently enabled or disabled. Capabilities are a per-thread attribute. Some of them are things like capsysadmin, capnetadmin, capsetpcap, or the more recent addition of capbpf. And they're somewhat self-descriptive, right? Capsysadmin is pretty much giving that process sudo access. Like that's pretty much the new root for all access for that given process. Capnetadmin is a subset of information, a subset of permissions. It gives you the ability to modify and manipulate network interfaces at whatever level you want. If you have the capsetpcap, then you could do things like trace files and stuff like that. You can actually do like packet captures. Now, one thing that's interesting, and I want to call this out, is that capabilities and syscalls and access that you grant to a given process is specific to the context in which that process resides. So if I have given a container running in a Kubernetes cluster, netadmin or libpcap, then that means that by default, inside of that container, if I were to exec in, I would be able to manipulate the network interfaces that container sees. but only that container sees. I wouldn't be able to manipulate the network interfaces that are happening on the underlying host because I don't have that view by default. Now, if I extended my pod definition to include net equals host, and I also gave myself net admin, then I can manipulate interfaces on the underlying host because I have put myself in the network namespace of the host by specifying net equals host, or hostnet true actually, in the Kubernetes pod spec. So all of these things are relative. Even cap sysadmin is mostly relative. It's actually a lot of permissions, and so there are some holes where you can kind of wiggle around and get out and maybe escalate your privilege. But at the end of the day, it's still relative. Like you're going to have a lot more luck manipulating those things that you can see within the namespaces that your process is spawned in. All right, that's capability. Let's jump in. We learned a lot about capabilities. Let's play with them. Let's see what we can do to actually do this. So here's an example of a pod spec that kind of aligns up with what I was talking about before. Say I wanted to give this particular pod net admin, and systime, but I don't want to give it any other capabilities. And so in this case, I can actually drop all capabilities and then grant only those capabilities that I think the application needs. And I'm providing access to those swaths of capability for that pod. So a container is just a process, a running process. If that process dies, the container dies. Processes can be given access to do stuff using capabilities. That access can be restricted using in a granular way, leveraging seccomp profiles. And we're going to talk about security profiles and here in just a minute. Security profiles can be used to allow or block any system call. When you define a security profile, you should use an allow and deny list, or you're going to miss stuff. We'll see some examples here in just a minute. So if I were going to explore security profiles, this is definitely the place to start. There has been a ton of research done on this recently, and a lot of changes in the Kubernetes ecosystem that enable you to define and both to discover what a security profile might look like, and also to define that security profile within your cluster and make use of it as part of your pod spec. Right here is a great jumping off point. sig.k8s.io, security profiles operator. And big shout out and props to Sasha Gunnert and Pablo Gomez and everyone else who's contributed to this project. I know that they're always looking for more people. Because not only can this actually be used to discover and enforce security profiles, it can also be used to configure AppArmor and SE Linux. Very cool stuff. I mean, if you're looking at really hardening your Kubernetes environments, this is the state of the art. So I was talking about security profiles. Here is an example of a security profile that I might apply to an application. And so let's just walk through it line by line real quick. It won't take long. So up here at the top, I have the default action. And that default action is set to SCMP act error no. And that means that any system call that is made that is not defined further down in this profile should just receive an error. I don't want that system call to happen. I actually have to call out the architecture that this list of names is going to apply to, right? Because it is a list of names. And so I need to have some mapping back down to the architecture. So in this case, this profile is going to map to the x86-64 architecture. And then here are a list of system calls that I want to enable for this particular application. I've got openat, lstat, capset, changedir, close, execve, or start up a new process. And for that list of system calls, I'm going to allow it. Now the challenge here is that there's not a lot of context, right? I'm providing openat, and at the end of the day, that means that I'm enabling this process to open files. But I'm not being very specific about which files it can open or in what way those files can be opened. Instead, I kind of rely on Linux's existing permissions model to do that, right? So if I'm running as not root and I have root-owned files and not root-owned files, then I can manipulate things that way. But it's tricky because when you're doing a seccomp profile, the syscalls that you give access to, you're giving carte blanche access for that syscall to that process. So one of the questions that comes up when I talk about this stuff is like, how do I understand like what permissions a process has? Like maybe I want to understand like what is possible for a process, like enumerate what it can do, right? And so this great tool written by Jesse Frizzell, one of my heroes, met her in CoreOS a couple years ago, who's doing amazing things with Metal these days, wrote a great tool called Am I Contained, and let's just take a look at what it does. So in this tool, I can actually run Am I Contained inside of a Docker container, Docker run bash, and then once I'm inside of that bash container, just the Docker run command. I can actually do Am I Contained, by pulling the binary down and running it, and I can see basically what it looks like, or what I can get away with as inside of this container or inside of this bash process. So this bash process has seccomp filtering turned on, and in so doing, it has actually blocked 63 system calls from my use. I can't make use of any of these system calls by default. Now, some things I can do, right? I can actually make raw sockets. I can make a bind. I can bind a service. I can set UID or set GID. I can set PCAP. These are the capabilities that I have been granted. If I jump over to a Kubernetes cluster and I do the same test inside of a bash pod running on top of Kubernetes, what does it look like? Very different, In this case, I see seccomp has been disabled. I'm still blocking some system calls, probably at the container runtime interface, at the Docker or containerd layer. And some of those ones I'm actually blocking are things like syslog, setsid, pivot root, swap on, swap off, those sorts of things. But this is significantly more permissive. And because of that, there's actually quite a lot more I can get away with here, because basically anything that isn't blocked is open to me, right? Pretty interesting stuff. So why are they so different, right? Well, these are so different because in the default Docker container, and the container I just ran on Docker, a seccomp profile was used. And this seccomp profile is generally referred to as the runtime default seccomp profile. It was developed by folks like Jez Fraz and Justin Cormick and quite a few others who continue to do a bunch of research into what a reasonable default seccomp profile might look like, and that reasonableness has changed over time. But specifically what it means, right, is that I want to define a list of system calls that any process would need to start up and run, but I don't want to make it so expensive that process can actually do anything, right? I want to actually limit it in a reasonable way. So what system calls could be considered dangerous, I should filter those out. And let's define a seccomp profile that allows us to make that filter. If you're interested in learning more, definitely check out this document on the docker.com website that really gets into the thinking behind it and some of the design, which I think is really good. It's a great read for this kind of stuff. So this runtime default thing, that sounds like an improvement in the security of our clusters. How can we make use of it, right? So one way that you can do that before Kubernetes version 1.19 is that you can use these annotations to set the runtime default as the seccomp profile to be used for your container at the container level or at the pod level. And after 1.19, that API became stable and it moved to the security context stanza of the pod definition. And so there, you can now just make use of the seccomp profile and the type, and you can set that type to runtime default, and that's how you can actually set it for that particular pod or container, just like before. But there's new stuff in 1.22, which I'm actually really excited about. And I think I did a session on this in cloudnative.tv on This Week in Kubernetes. And what we're doing here is that we're enabling a new flag in the kubelet that enables you to, it is configurable and allows you to set the default seccomp profile from unconfined, which is what it is by default, to runtime default. This means that if you're running containerd, Docker, or Cryo underneath the covers on your kubelet, that all of these will actually implement whatever their default seccomp profile is for any running pod on that kubelet, unless you specify something more specific in the pod manifest. So this is kind of a larger improvement for any pod running inside of your Kubernetes cluster. And as it matures, I'm really looking forward to seeing the adoption of this in different Kubernetes environments. Let's go back and take a look again. We are running inside of the Kubernetes pod with basically in an unconfined state. And we can see that we have not very many block syscalls, 22, and we have lots and lots of permission. And when I turn it on and I run that same mi contained command inside of that same bash process with runtime default applied, I see a different outcome. I see that seccomp is set into a filtering state and that the number of block system calls is quite a bit larger, which is an improvement in security. This is basically, think of this as an improvement in the model of least privilege, right? If your container doesn't need access to these system calls, then you should remove those system calls from that container's ability to call out. And that way, you can just make it so that like you're not providing more capability or more privilege to that container than it needs. All right. So there's another great piece of this, which I think is kind of really kind of bringing us up sort of to the state of the art again, with it as it relates to seccomp and security profiles and those sorts of things. And this is a pretty cool one. I got to see a great demonstration of this at eBPF Day at KubeCon this year, and they were talking about Kinvolk's inspector gadget, and one of the gadgets is a seccomp gadget. And what this does is it allows you to instrument the app with an annotation and or label, and then the gadget will use eBPF to inspect all of the system calls that this particular process makes over time and make a list of them and basically generate you a seccomp profile. And it can output that generated seccomp profile as part of as something that can be consumed by that Kubernetes security profiles operator that I mentioned before, right? A great place to jump off. That is pretty darn cool. So this gives you the ability to record and generate a seccomp profile and then consume that seccomp profile leveraging the profiles operator, which in my mind is like pretty much end-to-end an improvement in your security. If you wanted to harden those applications and understand a place to start, this is it. It's really cool. Now, sometimes what we need is just a little bit more context. And eBPF and tooling, as I've mentioned a few times, and tooling that leverages it can provide a lot of context about what's actually happening within your cluster. What if I told you that you could get way more context about what's happening in your clusters from both a networking perspective and also a process perspective with Cilium? Let's check out how that works. All right, so here I have a Kubernetes cluster operating. I've got a few different nodes. I've got a few different applications running, kubectl get pods -a. And I've got Cilium deployed as my CNI. And so, because Cilium operates at the eBPF layer, there's a ton that we can do, right? We can actually give you a view of network events that are happening within your cluster. Let's take a look at Hubble here, which is actually one of the ways that we expose this information. If I do Hubble observe -n, say my tenant jobs namespace, I can see traffic moving back and forth between pods within that namespace, querying things and getting along and interacting with stuff. And I can even, for example, I can prove that this is somewhat dynamic, right? Let's actually take a look at a visual representation of what I see here, right? So I'm going to jump over to the Hubble UI. So this is the Hubble UI, and it gives me a view of what's actually happening inside the cluster, and I can see all of my applications interacting across the entire cluster, and I can see these network events, just like I saw in the on the other side of things, new network events that are coming in. Let's jump back over here and we'll just do this. We'll do kubectl exec ti-n kube system, actually tenant jobs crawler, and we're going to curl yahoo.com. And we saw that it was redirected, and that's good. And there are our flows that are coming out, right? So now I can actually see the flow information moving back and forth between the crawler application and core DNS. So here's my query for yahoo.com, yahoo.com.lan, yahoo.com. Actually, if I look further up, I can actually even see all of the different queries that yahoo.com resulted in on my DNS servers, right? When I do a curl of yahoo.com, it actually tries to resolve it as yahoo.com.cluster.local, service.cluster.local, all of those things. But eventually it does resolve it to an IP address, and then it actually tries to connect to it. And I can see the identity of the pod that is actually making the call. I can see the destination. And if I go back to my UI, I can see all of that information visually again, right? So before, when we looked at this, we did not see yahoo.com, but now we do, right? So this is an example of leveraging BPF to give you a very holistic view of what's happening with network event data across your entire thing. And as we can see from the Hubble side of things, it looks like we're actually like doing a TCP dump almost. But we're doing that TCP dump across the entire cluster. So we can actually ask Hubble all kinds of interesting questions, like show me all of the FQDNs that were reached. I can like show me the new URLs that propped up in the last 6 months, and all kinds of interesting things like that. Now, just like the system call interface, there's other stuff we can do with BPF as well. One of the things we've been working on is this process tree ancestry stuff. This is an example of me interacting with a pod and starting up and spawning a new process within that pod. Now, I know this may not be super visible because the text is kind of light, but maybe I can highlight it. No, not really. Let's see. Yeah, I guess that's a little better. Anyway. So what this is actually showing us is process tree ancestry. And this is a neat thing because what this does is it gives you an entire view of the running process and all of the things that it has done. And we emit both this network data and this process data as events that you can throw into Splunk or a SIM integration or what have you and query over time. And this gives you the ability to understand basically the export of all of that relevant metadata from BPF can be exposed in a way that you can consume it and make use of it over time. Really super cool, and also gives us the ability to kind of build like really powerful queries about what's actually happening in your cluster. Now, that's some of the stuff that Cilium can do. The last thing I'm going to tell you about that we've been really kind of excited about on the BPF front is that we've actually been working on a thing called tracing policy, which gives you the ability to actually do a couple of different things, right? So with tracing policy, we can set up a K-probe that watches for particular system calls. And when it sees them, it can report them back into and expose them as an event to just generic system call watching. And you can actually get a lot of the context about that generic system call exposed. So if you're watching for open@, for example, within your cluster, or within a particular subset of pods, matching by label or within a namespace or what have you, then we can show you all of the files that were opened by any process within that namespace or target over time. And then you can actually use tracing profiles to change the match action. So maybe I don't want to log it. Maybe what I want to do is log it and kill it, right? So in this example, I've actually written a tracing profile that whenever it sees somebody try to make the sys mount call inside of a containerized, inside of a container, I want that container to be killed, right? I'm actually going to send a sig kill to that container process if it tries to make a mount call. And so in this way, we could easily kind of get into this loop where we're doing detection, we see what we want to harden, and then we use profiles like this to harden it. If I see a violation of particular rules that I see, that I expect to be followed within my cluster, I'm going to terminate your process. And this is all done with eBPF. And in my opinion, again, this is just absolutely the state of the art when it comes to how do you secure, model, and observe and harden your applications in a Kubernetes and containerized environment. Really, really cool stuff. And with that, I thank you. I'm Maui Lion. I'll be on the chat. And if you have any questions, please throw them in the chat. I'm happy to answer. And if you have any other feedback for me, just let me know. Thank you so much. I'm everywhere as Maui Lion.